I will go through just a few more problems from chapter 34 before your homework is due. Number 70 is about using a converging lens to project an image of a movie slide or film slide, or that just be a piece of film, whatever. Project an image of a slide onto a screen. And what we're told is the magnification. So let's draw a schematic ray diagram. This won't have accurate distances. It turns out that the distances involved in this problem would make it difficult to actually draw. It would be difficult to fit onto a page. So here's a crude drawing of a lens with an optical axis. And the movie slide is over here, let's say. And we know that it needs to produce a real image on a screen over here. It's got to be a real image, because if you're the person sitting in a seat here looking at the screen, if there's no light actually striking the screen, if there's no rays converging and forming an image on the screen, then you won't see anything. And that means that this object needs to be outside the focal point. So I will just draw a couple focal points. 1, 2, 3, 1, 2, 3. And this drawing is not based on the actual distances in the problem, but we know that for a thin lens, this ray that goes through the center of the lens is undeflected. We know that a ray coming parallel to the optical axis, when it gets to the center of the lens, it will refract through the focal point, and we know that a ray that goes through the focal point will come out parallel. Okay, so this drawing didn't come out at all the way I expected. I was hoping that the image would be way over here. You know what, I can redo it quickly, because this actually demonstrates a characteristic of lenses that's worth noting. This time, I will put the object closer to the focal point. Let me go with the focal length of 1 centimeter here. Okay, if you put the object closer to the focal point, your image will tend to come out farther from the lens. So this time, put the object here, and let's see what happens. First principal ray, I'll draw a parallel. It's refracted. Oh, that's, that doesn't work so well either, does it? Let me try 2 focal points which are farther from the lens, like, here we go, 3 centimeters on either side. Now if I draw my object here, let's see what happens. This time it would refract through this focal point, and an undeflected ray would go like this. Now we're talking. So I just needed a longer focal length. And a ray which, well, this one's very awkward, but a ray which goes from here through this focal point. So I have to extend the vertical line that represents the lens and look at a ray that goes through this focal point. When it gets to the lens, remember this vertical line we think of as the lens, it will come out parallel. Okay, good. So now you get a sense that these 3 principal rays will converge pretty far from the lens, and our screen would have to be somewhere off the page. First thing you'll notice is that the image is inverted, it's upside down, and that means that the magnification is a negative number, but we're given, what are we given? We're told that the image needs to be 98 centimeters high. So H prime is 98 centimeters. Sometimes your book, I believe, uses a Y, and sometimes they use an H for the image height. And I suppose technically that should be a minus sign because it's an inverted image. And the slide itself with the image that's producing, or excuse me, I'm making the word image do double duty. The picture on this movie slide, the picture is 2 centimeters high. So the object height is 2 centimeters. And that immediately tells us that the magnification is negative 98 over 2. Let's see, 45 plus, what is that, 49? I'm embarrassed that I have to check, but just be sure. Okay, that's a magnification of negative 49. It's dimensionless because it's centimeters over centimeters. What can we do with that? Well, remember, there are two ratios which are equal to magnification. Magnification is also negative s prime over s. And remember, that minus sign accounts for virtual images versus real image. We're talking about a real image over here, that these rays really do converge right here, which means that my image distance, not image height, but image distance, s prime, is a positive number. Negative positive tells us that the magnification is negative, as it is. Okay, well, we already calculated m. They gave us the two heights, so we know the magnification, or the desired magnification, and that means that we can calculate s prime in terms of s. So s prime would be negative ms. Well, that's negative 45, or 49. Remember, m is already a negative number, so 49s. Okay, the other thing we were given is this total distance, and of course this is cluttered now, but from the object all the way to the image is 300 centimeters. We're told that the distance from the slide to the screen is 300 centimeters. So what's free to move is the lens. It's going to be up to us to move this lens back and forth until all the distances satisfy the thin lens equation, and we get the image at the desired distance. Because remember, if you left the slide fixed, the movie slide, which is the object, and you move the lens around, you're going to change the location of the image. We want the image to be right at the screen. We want it to be focused in that focal plane. So what we also know is that s plus s prime is equal to 300. The total distance from object to image would be the object distance plus the image distance. Well, now we can substitute this. S prime is the same as 49s, so that means s plus 49s would have to equal 300. In other words, 50s is 300, and now that's trivial. Chop off a 0. The object distance would have to be 6 centimeters. Now, what they're actually asking for in part A is what's the focal length? So let me move to another sheet of paper here. Find F. Well, we just found that the object distance is 6 centimeters. That slide needs to be mounted 6 centimeters from the lens of the projector. And the image distance we just found would have to be 49 times 6 centimeters. It needs to be 294 centimeters from the lens. And that checks out, right? 6 plus 294 is the 300 centimeters total between the slide and the screen. Well, now that we know S and S prime, we can use the thin lens equation to find the focal length. And you could do the this method. F is equal to S prime over S plus S prime. But you know what? I think in this instance, because S prime is such a large number, it's easier just to use the reciprocal button on your calculator, at least if you have this $10 Casio like me. So let's see, 6 centimeters reciprocal plus 294 reciprocal equals, I take the reciprocal once again, and I find that the focal length is 5.88 centimeters. Okay. So actually, I suppose I misspoke slightly when I talked about where we would have to put the lens. In this problem, we don't have, what's under our control in this problem is the focal length. We're supposed to choose a lens with the appropriate focal length. I was thinking that the focal length would be given and that we would have to slide this back and forth until the image is focused. If you look at the equation, the thin lens equation, if F is already determined, then, and one of these is fixed, then what you have control over is the other. And notice if you were to slide this lens back and forth, if you slide it forward, didn't you just increase S? And of course, if you increase S, you're going to change S prime as well. So how you go about solving the problem is determined by which quantities are fixed and which you can change. How far should you place the lens from the slide? That's part B. Well, again, that's already been determined. The distance between the lens and the slide is fixed. That's the object distance, which we determined to be 6 centimeters. So that's kind of, I'm trying to look at this whole problem overall and what we have control over here. And it seems that by saying that the slide has to be 300 centimeters from the screen, and by specifying the magnification, everything is already pinned down. Like there's only one focal length that works. I'm wondering now, is it possible to use a lens with a different focal length and achieve the same setup? I don't think so. What the equation, what the equation has told us, or equations have told us, is that there's really only one focal length that works, and there's only one lens object distance that works. Those are the only numbers that plop out. So if the problem had said, okay, the object has to be 300 centimeters from the screen, the slide is 300 centimeters from the screen, and that's the only thing that's specified, just that you want a real image, then you would have some freedom to tweak these parameters here. I suppose you could choose any focal length you wanted, but that would also determine where you put the lens. In this case, because the magnification has been fixed, it turns out only one focal length works and only one object lens distance works. Okay. Just in case it wasn't clear, your image is way over here and it's upside down and greatly magnified by a factor of 49. So if this slide were part of an old Western film and you had a little picture of a horse on this tiny slide, the image of that horse would show up much larger on the movie screen, and you'd be sitting somewhere in here. Well, let's face it, if you got to the movie late, you'd be sitting right here, and your neck would hurt when you left the theater. But if you got there early, I don't know. For me, this is where it's at. That's if I'm willing to pay $20 or whatever it is to see a movie now. Who does that after we have Netflix? This problem is kind of neat. It's the very next problem in the book, number 71. It was not part of your assigned homework. You've got a plano-convex lens, which is being used to focus an image of an object which is initially 50 centimeters from the lens. And this material from which the lens is made, it's got an index of refraction of 1.5. But supposedly it's made out of a special material. This is called an electro-optic material. And if you were to apply an electrical voltage across the material, you would change its optical properties. In other words, you could change the index of refraction. That's kind of neat. So instead of swapping in a lens with a different focal length, you could simply change the properties of that same lens. And if you've changed its index of refraction, you're probably also going to change its focal length. So the idea is, initially this lens is focusing the image at a particular distance, and you would like to cause that image to scoot back 5 centimeters closer to the lens without changing the initial object distance. So normally if you wanted to change the location of the image, but nothing was changing about the lens, you would have to move the object forward or backward, and that's going to make the image move around. In this case, we're actually changing the properties of the lens. So let's first figure out where this image is initially, because if we want to know where it is after it scoots back by 5 centimeters, we have to know where it starts out. And that means we're going to have to use the thin lens equation to find S prime. But in order to use the thin lens equation, you also need to know F. Remember, 1 over S plus 1 over S prime equals 1 over F. We do know the object distance initially, it's 50 centimeters. We don't know the image distance, that's what I would like to find, but we also don't know the focal length. We can find the focal length using the lens maker's equation. Remember, lens maker's equation depends on the two radii of curvature. Okay, so the reciprocal of the focal length is n minus 1. I'm going to call it n naught because I'm acknowledging that in a moment we're going to change the index of refraction of the lens times, and it just goes from left to right, 1 over R1 minus 1 over R2. I'm not going to lie, I'm cheating and looking at the equation. I sort of have it memorized. You know, if you're going to have it memorized going into the exam probably because you will have done enough homework problems. The difficulty is being careful with the signs of R1 and R2. So since we've got our object over here, let's look at the lens from this direction. The left face of the lens is convex towards the object, so it gets a plus sign. We consider this to be a positive number. We're told that the radius of curvature is 15. So this face of the lens is part of a larger circle with a radius of 15 centimeters. Now, R2, remember, a flat surface is the limiting case of a circle with infinite radius. So R2 is infinity, and we don't even need to worry about it. So this is going to be 1.5 minus 1 times 1 over 15. And I've neglected to write the units there, so we've got 0.5 divided by 15. The focal length is 0.033 repeating. Now hang on a second. Why is your book saying, oh, that's the reciprocal of focal length. Yeah, see, don't make that mistake. This is the reciprocal of focal length. So hit the reciprocal button. Focal length is 30 centimeters. Okay, I'm going to call that F naught. That's the original focal length. We're going to change the focal length in a moment, not by swapping out the lens, but by changing the optical properties of the lens. The idea is to apply voltage and change the index of refraction, the effective index of refraction. Now that we know the focal length, we can find the original image distance, which I'll call S prime naught. Okay, so 1 over S naught prime is equal to 1 over F minus 1 over S. And I'll put subscript zeros on all of these. See what I did? I solved the thin lens equation for 1 over S prime. And you'll notice I don't actually need the focal length, I need the reciprocal of the focal length. So I didn't really have to get this number. I could have just left this in my calculator, maybe stored it in memory. Okay, so here's what I'll do. 30 reciprocal minus 50 reciprocal equals, take the reciprocal once more, and the original image distance is 75, which means that my diagram does not accurately capture what's going on here. This focal point is probably closer to the object, and that would put the image way over here. The image distance is actually greater than the object distance, but that's okay. We're not using the diagram to calculate anything. Now the new image distance, and let's check, should S prime be a positive number? Yes, it's a real image. Real images are associated with positive image distances. New image distance, I'll call that S1 prime. Well, we're told in the problem that the person would like to scoot the image back 5 centimeters closer to the lens. Right, which would mean that the new image distance needs to be 70 centimeters. Nothing has changed about the object distance. So S1 is equal to S naught. That's still 50 centimeters. Okay, so now we know, we look at the thin lens equation. We know the new object distance, it's the same as before, 50 centimeters. We know the new image distance, that's the 70. We'd like to know the new focal length. So we say that 1 over F is equal to, I'll call it 1 over F1. This is the new focal length. 1 over S1 plus 1 over S1 prime. And what I'll do is actually solve for the reciprocal of focal length, because we're going to go back to the lens maker's equation and use it to find the new index of refraction. We don't actually need F, we just need 1 over F. Okay. So 1 over S plus 1 over S1 prime, that would be 50 reciprocal plus 70 reciprocal equals, and let me keep a few digits, 0.0342A. I'll put that in memory. This is the reciprocal of the new focal length. And now I will go back to this equation to find n. By how much would the index of a fraction need to be increased? That's what they're actually asking. So let's find the new index of a fraction. Flip this over. That's the best way to do this. Yeah, there we go. All right. Well, let's apply the Lensmaker's equation again. That's going to be n1 minus 1. This is the new index of a fraction times 1 over r1 minus 1 over r2. Well, remember, R2 is still infinity. We haven't changed the shape of the lens. We've only changed its optical properties, namely the index of a fraction. So if I solve this for n1, I find that n1 has to be R1 over F1 plus 1. I believe I've done that right. Well, R1 is 15 centimeters, and I'm just going to multiply that by the reciprocal, which I already found, and store it into memory. So 15 times memory recall, that's 1 over the focal length, plus 1. The new index of a fraction needs to be 1.5143. Okay, so the change, oops, not n2, n1. The change in the index of a fraction would just be a modest, you take that number and subtract the original 0.14. Now, I'm going to call this percent delta n. That would be delta n over n naught times 100. So if I take that change and divide it by the original index of a fraction of 1.5, let's see here. Let's see. So I think that would be 0.9%, which is roughly 1%. I believe I did that right. Times 100. Right. Okay. A roughly 1% change in the index of refraction of this material. I don't know how reasonable that is for these so-called electro-optic materials, but generally speaking, 1% isn't a huge change, so maybe that would be achievable. Number 78 is another problem from your chapter, which was not assigned, but it's worth taking a look at. In this problem, you're supposed to prove the property of a concave spherical mirror, which allows us to use the mirror equation. Remember, the mirror equation looks identical to the thin lens equation. So all I've done is use my heavy-duty industrial protractor compass, this is a compass, to draw an industrial strength heavy-duty circle. This is the radius of the circle here. That was the center of curvature. And we're supposed to prove that the focal point of this mirror is, in fact, 1/2 the radius of the curvature, or the radius of curvature, which would put the focal point right about here. And it's really not hard to do this. The proof only depends on one assumption, that the rays you're talking about are paraxial. So let's look at an incoming parallel ray, because remember, the focal length, by definition, is the point at which incoming parallel rays are converged. I'll just start with a single ray. This one looks good. This is going to bounce back, pass through the optical axis. Another parallel ray would come in, bounce back. And the idea is you could draw as many of these rays as you want. As long as they're parallel, you would find that they all converge through approximately one point. That's called the focal point. Now, if you apply the law of reflection very carefully using a protractor and a thin pen and a ruler, you would find that the rays don't actually pass through a single point. They cluster around a single point, but it's not perfect. And that's because a spherical mirror does not have to be the desired behavior. It approximates what a parabolic mirror would do. So if you took a parabola and rotated it about its axis, you'd sweep out a paraboloid. And a reflective paraboloid really would take incoming rays and focus them at a single point. Well, a spherical mirror does a pretty good job of that. And you can see why. If this is a parabola, there's an osculating circle, I believe it's called, that fits nicely into that parabola. So as soon as you go beyond the edges of the circle. Once you're over here and here, this parabola does not behave the way the sphere does. But for incoming rays like this, a parabola really would focus them all through a single point. That's called the focus, coincidentally. And you can see that as long as you have a small section of a spherical mirror, it's going to do what a parabolic mirror does. Light that reflects off these sides of the spherical mirror, it's not going to do the same thing that a parabolic mirror would do. Okay, so back to the geometry here. I'm just going to very lightly trace the normal here, just a little piece of the normal, so I can more easily visualize the reflected ray. We know that the reflected ray has to make an equal angle with the normal, so it goes off like this. Okay, we know the focal point is going to be somewhere on the optical axis. The question is where? Is it here or here? Well, presumably it would have to be here. That's the only place where this reflected ray passes through the optical axis. So if I drew a ray over here parallel, it should bounce through the same point. If I drew a ray here parallel, it should also bounce through this point. We just need to find what is that point. Now you can already tell, because I was careful to make the reflected ray equal to the incident ray, you can already tell that it looks like the focal point is about halfway out from the mirror to the center of curvature. We just need to prove that now. And we will be looking at a right triangle. Okay, I'm going to draw a ray. Well, think about it. If this really is the normal line, isn't the radius of a circle, I drew a radius from the center of curvature outwards, doesn't a radius always intersect a circle so that it's perpendicular to the tangent line? Well, what else is perpendicular to the tangent line? By definition, that's the normal. So this normal line actually passes through the center of curvature. It has to, because if this line really is perpendicular to the tangent, then it's along one of the radii of the circle. It should go right through the center of curvature. And now we have a triangle. We've got this triangle right here. Okay. Your book calls this angle phi. This is the angle that the normal makes with the optical axis. And we can see just from geometry, so you've got two parallel lines. This ray and the optical axis are parallel, which would make these two angles alternate interior angles. This angle has to equal this angle, so I'm going to call this phi as well. That's just geometry. Back to the optics. What do we know about this angle? Well, from the law of reflection, these two have to also be the same. So this is also phi. And I want to point something out. I think a number of you are getting Snell's law mixed up with the law of reflection. When you're dealing with reflection, you don't care at all about index of refraction. It doesn't enter into the discussion. It doesn't matter what material this mirror is made out of, or whether your rays are passing through air or glass, whatever. Even if this reflection was happening underwater, these two angles would still be the same. It has nothing to do with the index of refraction. Okay, if these two angles are the same, aren't we dealing with an isosceles triangle? That means this side has to equal this side. Those two sides are equal. How about we just call them A? Each of these sides will have a length A. Side length A, side length A. What is the length of this other side? The distance from the circle, which represents the spherical mirror, to the center of curvature. That would be the radius of the sphere. So now we can apply some equations from trigonometry. Why don't we apply the law of cosines? Yes. So I'm going to use these two sides, this side, and the angle between them, to calculate this side. Law of cosines says, this is something you may not have memorized if you don't use it often, but this side squared, a squared, should be equal to this side squared plus this side squared. It's kind of like Pythagorean theorem, but you have this third term, minus 2RA times the cosine of the angle between them, which is phi. Okay, so third side squared equals the sum of the squares of the other two sides. That's like Pythagorean theorem, but now you have to do this third term, subtract 2 times RA cos phi, which is the angle between those two sides. Now we just simplify. It looks to me like we've got an a squared on both sides. So now we have 0 over here. In other words, 2RA cos phi is equal to R squared. I think we're solving for A here, are we not? Yeah, because if we could figure out what A is, wouldn't we know what this distance is? What's this total distance from the center of curvature to the mirror? That is also the radius. So whatever this is, subtract that from the radius to find the so-called focal length, the distance from the mirror to the point where the rays converge. Okay, so I'm going to go up here now and solve for A. Well, we can divide an R from both sides of the equation, and I find that A is equal to R over 2 cos phi. And we're almost done. Remember, usually when you're using a spherical mirror, you're not using this much of the mirror. If I just chop it right here and here, this might be the only part of the sphere that actually shows up in the mirror. It's just a small section of a sphere. And that means that any rays which actually strike the mirror involve a small angle phi. So for paraxial rays, and in most applications, the images are formed by paraxial rays. What do we know about a paraxial ray? Well, this ray has to be fairly close to being parallel to the optical axis. In other words, it's a small angle. Phi is small. Phi is close to 0, and that means the cosine of phi is roughly 1. That's something you should just memorize because it shows up all over the place. When you look at the cosine function, cosine drops to 0 at 90 degrees. Well, at the very beginning of the cosine function, it's practically flat. There's a range of angles here where the cosine function is really close to 1. It doesn't start to dip down until right about here. So there's a significant range of angles for which the cosine of theta is approximately equal to 1. And that means A is equal to R over 2. Approximately equal to R over 2. So there you go. If this is R over 2, this must also be R over 2. The focal length is R over 2. That wasn't hard to prove. We just needed the law of reflections. We used a little bit of geometry, the law of cosines, and then the recognition that for small angles, the cosine of phi is roughly equal to 1. Okay, now be aware. Let me do a quick drawing for you here. If this was an actual spherical mirror, if I think of this as my optical axis, then I'll draw some rays coming in parallel. And we know that they're all going to converge roughly through a single point. Oops, we'll call that the focal length. Okay, so maybe this is your spherical mirror. Maybe you've got, there's a star or a planet that you're looking at very far away. So maybe this spherical mirror is part of a telescope which you've mounted and pointed at the moon. And so all these light rays are coming from the moon and converging to this single point. Well, often this other direction perhaps is Venus. Maybe there's another bright object in the sky off in some other direction. And then there's no reason why you can't think of, let's see, if the radius of curvature is here, I could now think of this direction as the optical axis. Wow, this picture's super cluttered. I'm sorry about this. What if I look at another set of parallel rays coming in from another direction, like Venus rather than the moon? Well, these rays will also converge through a single point. But if you were very careful in making this diagram using a protractor, you would find, and you probably can't tell so well from my picture here, but these 2 points actually do not lie in a plane perpendicular to the optical axis. So if I draw a perpendicular line through my original optical axis, here's my original optical axis. Here's a line representing a plane that cuts perpendicular to the original optical axis. Well, rays coming in from this direction, parallel rays, would actually converge at a focal point slightly in front of this vertical line. So this could be called the focal plane. And bundles of rays which are coming in paraxial, any bundle of rays that's more or less parallel to the original optical axis, those bundles of rays will converge to points on the focal plane. But if you're looking at rays coming from a decidedly non-paraxial direction, they will focus out of that plane. And that's the effect called spherical aberration. So the lens doesn't behave exactly as we would like it to. Maybe you have a sense that the smaller the section of the sphere, the less of a problem that would be. But basically, you can only focus object points into image points if they're in a relatively narrow field of view. So it would be difficult with a simple concave mirror like this to produce a nice sharp image of a large swath of the sky. You kind of have to be imaging a relatively small field of view. And I'm no expert in optics, but there's a lot more to be said about these topics for people who manufacture and design lenses. You'd have to take this and much more into consideration. The one remaining optical element, simple optical element that we didn't talk about is the convex spherical mirror. I believe this shows up in your homework. Your book addresses it very briefly. The nice thing about this mirror, just like the concave mirror, is that there's no new equation to memorize. You can still use the thin lens equation. Of course, in this context, you would call it the mirror equation. You just have to get some practice with the principal rays. I actually went through this whole thing already, and I forgot to hit the record button, so here I am again. Convex spherical mirrors, they're fairly ubiquitous. You encounter them all the time. When you look at the side view mirror in a vehicle, that is a convex spherical mirror where you're looking from this direction. It's not obvious that that mirror is convex, but if you look at it from the side, you may be able to see the curvature. And it's going to take an object way over here, like a truck, which is in the lane to your right if you're driving on the highway, and it will produce an image of that truck on the other side of the front surface of the mirror. That image will be reduced in size, and it will be a virtual image. Security mirrors in 7-Elevens, for instance, if you walk into a convenience mart, you see those big circular mirrors mounted in the corner of the room where you can see almost the entire room. Everything's just reduced in size. That's a virtual image formed by a convex spherical mirror. And my favorite would be the reduced virtual image that you see of yourself when you look into a Christmas tree ornament, or let's see, a polished brass knob on a drawer or a cabinet. Have you ever been in a room and suddenly realized you can see yourself, I don't know, a dozen times in all of the polished brass knobs that you see on the various drawers within the room? So convex spherical mirrors, they're common. Okay, so I've used my heavy-duty protractor compass. I keep doing that. My heavy-duty compass to make a heavy-duty circle here, representing this convex spherical mirror. And just like for a concave mirror, the focal point is halfway between the vertex of the mirror and the radius, the center of curvature. Now I've measured this with my ruler and determined that it's about, the focal length from here to here is about 4.5 centimeters, but I gave it a minus sign because convex mirrors are considered to have negative focal lengths. It's that sign convention that allows us to use the thin lens equation for the mirror equation. So if you want to stick with one equation for every scenario, 1 over s plus 1 over s prime equals 1 over f, you have to observe sign conventions. Just like a diverging thin lens, a convex spherical mirror has a negative focal length. And one thing that should help you remember that is the connection between virtual images and negative focal length. A diverging lens always produces a virtual image, and it has a negative focal length. By the same token, a convex spherical mirror is always going to produce a virtual image. It has a negative focal length. Okay, As for the principal rays, well, let's just do an example. I went with an object that is 8 centimeters from the mirror. That's from the vertex. But notice I've drawn a vertical line. You don't actually need to draw this curved surface of the mirror. Use a vertical line to represent your mirror, just like you did for a thin lens. And I measure the height of the object to be something like 7 centimeters. So I'm going to find where the image is, that's the image distance, and also what's its height using two methods: ray tracing, that's what this diagram is about, and also just the mirror equation. Okay, so the first ray that I've drawn, that's the easy one. We know that it'll bounce off the mirror at the same angle at which it came in. That's the law of reflection. So I used a protractor to make sure that this reflected ray made the same angle with the normal as the incident ray. And notice in this case, the normal is the optical axis. The second ray that I'll draw, the second principal ray, here's how it works. Draw a ray coming in parallel to the optical axis, and I know that this ray is going to bounce off the mirror so that it appears to be coming from this focal point inside the mirror. Okay, so I line up my ruler with the point of incidence and the focal point, and I have this ray reflected off like this, and I will extend it backwards right now to show that it appears to be coming from that focal point. And again, you may be thinking, wait a minute, you did not use the law of reflection here, because the angle of incidence on this vertical line would actually be 0, and yet it's bouncing off at some non-zero angle. That's true, but remember, we're only using the vertical line to represent the mirror. In actuality, this ray would bounce off the curved surface of this mirror in such a way that the law of reflection would be obeyed. So don't get hung up on the details there. Truthfully, a ray this far from the optical axis would not actually behave in this way. Only rays somewhat near the optical axis would do what we pretend that they do using this model. Okay, I think we've already located the image. This ray and this ray, they've both been reflected off the surface of the mirror, but they appear to be diverging from a common point here. This would appear to be the image point corresponding to that object point. But we would like to have a third ray to confirm that location, and it's really just the opposite of this ray. A ray coming in parallel will bounce off as if it came from the focal point. So instead, what we'll do is aim for the focal point, draw a ray headed towards the focal point. Here's where it's going to bounce off, but I will extend this line. Wait, I don't know, bad, very bad. I wish I could get rid of this, but I can't because it's pen. It's going to bounce off parallel, as if it came from somewhere back here. Ooh, good, that actually worked out. Okay, so this third principal ray that I've drawn right here is the opposite, in a sense, of this one. Instead of coming in parallel and bouncing off as if it came from the focal point, well, wouldn't this ray do the same thing? It's coming in parallel and bouncing off as if it came from the focal point. I just reversed the order. Aim for the focal point, but when you get to the mirror, that's the vertical line, you reflect parallel to the axis. So I have now located the image. First thing you should notice is that it's upright. So this convex mirror produces an upright image. That is why in Home Alone 1, when Macaulay Culkin is standing in front of the Christmas tree, he sees a reflection of Marv and Harry standing just outside the window. And in that reflection, they're upright. The two robbers are upright, the sticky bandits are upright, and they're reduced in size. It's an upright virtual image. And I know it sounds like I've watched Home Alone 1 recently. And that's because I have. I don't care if it's spring. I'll watch it in the middle of summer. But you've got a reduced image. It's upright. It's a virtual image. Of course, there are no rays actually converging here because that's behind the mirror. They just appear to be diverging from that point. That's a virtual image. Okay, according to the diagram, my height is 2.5. Height of the image is 2.5 centimeters, and the distance of that image from the mirror would be something like 2.8. Okay, and I'm going to be honest, here's where I forget. Is that a negative image distance or not? It is a virtual image, so I expect it to be negative. I'm going to squeeze in a minus sign there. But the other equations that we have at our disposal will confirm that. So that's using ray tracing. The magnification here would be h prime over h. That's 2.5 over 7. 0.36, roughly, 0.36. Well, as a quick check, I can take my image distance and divide it by object distance. Let's see what I get. I'm going to take the absolute value. 2.8 divided by 8 is 0.35. Very close to the number I just calculated. So let's a check here. It's the same old equation. Okay, 1 over s prime would then be 1 over f minus 1 over s. Okay, I'm going to use the reciprocal button. Here's where I must observe proper signs. The focal length is considered to be negative 4.5. So I'm going to go 4.5 with a minus sign, hit the reciprocal button, minus an object distance of 8 minus 8, hit the reciprocal button, equals. Lastly, I'll take the reciprocal of that. And this tells me that my image distance is negative 2.88. All right, really close to what I got from the ray diagram. So it appears that, yes, the image distance is considered to be negative. Remember, don't confuse this with the thin lens, a thin converging lens. For a converging lens, if your image showed up on the other side of the lens, you would consider that to be positive because it's a real image. In this case, the image is also on the other side, but this time it's on the other side of a mirror. It's a virtual image. That's why the image distance is considered to be negative. Okay, and so that means our image height should be magnification times object height. Well, magnification is negative s prime over s times h. We were given this number, we calculated this number, we were given this number, so here we go. Negative 2.88 over an object distance of 8. That's the magnification. Notice it comes out positive, it's an upright image, times the object height of 7. So without ray tracing, just using the equations alone, I find 2.88 divided by 8 times 7, that the image height should be 2.52 centimeters, which is pretty darn close. You know, for two sig figs, they agree exactly. That's really nice when your ray tracing gives you the same results as the thin lens equation. Okay, so get some practice with all four. There's two types of thin lenses, converging, diverging. There's two types of spherical mirrors, convex, concave. Get some practice, get familiar with the sign conventions, but probably should have those rules nearby when you're doing homework problems or exam problems. And from now on, we can do some slightly more interesting things by combining optical elements, like two lenses together or a lens and a mirror, and look at optical systems like the microscope, the telescope, your eyeball, corrective lenses, and I'm tapped, but there are many more examples.